if you put identity here, the inner product, since I have taken a unit vector, I would get 1. And P per P is just I minus P, so of I minus P, so which is 1 minus, if you put I minus P here, you just get 1 minus P, which is 1 minus P. All these things are fine. Okay? You get this linearity also, obviously. Right? You just put P on plus P2 here. So this is a nice example. The main thing is the non-negativity, right? And mu of identity is 1. So once you have this example, you can take convex combinations of such things. They also would give us examples, right? I can take 2 of them, some one coming from U, another coming from so mu of U, say some alpha times this, times 1 minus alpha times mu of V t for some other unit vector. I can take such a convex combination, alpha between 0 and 1. That also will do, right? So you can do more general things, get examples. So to do that, I write the same thing in a different way. So this mu of P is U P U. So if I look at the projection onto U, so this onto U means the space spanned by U. Okay. Our notation for that is this U. Okay. The projection onto the space spanned by U. So then this one I can write as trace of U times P, or same as trace of P times U, either way. This is a small exercise.
So, sorry Rajan, what is this notation I always get? This is physics kind of notation.
Yeah. What does it mean? It just means so the generally.
Obviously confused.
Yeah. So xy. You just think of it as xy star. Okay. Like this. For x to xn. Y1 y2 yn. So this is the ijth entry is xi yj bar. Okay. So that is what it is. xy is xy star, and our inner products, okay, inner product between x and y is x star y. Okay. So the inner product is antilinear in the first variable. So inner product between x and y is x star y. Okay. With that understanding, this is just this. So this UU is the matrix where the ijth entry is ui uj bar. And that you can see is the projection onto the space spanned by U.
Rank 1.
Rank 1 projection, whenever U is a unit vector. Okay. Now, if I take any such xy, okay, and you take an order. X times xy. Okay. If you do this, so as I said, this is just xy star. So this is same as xx y. Okay. And the trace of that. So this is a rank 1 operator. Okay. So the trace of this, you write the things and add up, and you just see that it is just y x. Okay, you just write it down.
Yeah, just
and add it up. And you see that this is.
Or use the fact that trace of AB equal to trace of BA.
Yeah. So So this is the general formula for any x, right? This is true. Okay. You just have to write it down and expand it. So this is same as this. Okay. I'm just writing this UPU as trace of this. UU times P or P times UU, either way. Okay. Trace XY is same as YX.
X is what operator.
For any operator X. So I have operator P there, but any operator X times a rank 1 operator like this is actually just this. Another rank 1 operator, XXY. And the trace of that is given by this is the trace of a rank 1 operator like this, Xi, Yj bar, is the sum of the diagonals is summation Xi, Yi bar. So that is the inner product between Y and X. Right? So it is the inner product between this and this. Okay? So X has been replaced by XX. That's all. Okay? So let us forget this now. I'm just writing it. That way it was easy to compute. It was like this. Okay? Mu of P is trace of this projection onto the space spanned by U times P. Okay? The same thing I have written in a different way. So more generally, what I can have is that I can have a mu of P as trace of some rho times P. Okay? I can take convex combinations of such things, and generally I would get trace of some operator rho times P, and what should be this rho? Rho should be positive and trace rho equal to 1. So these are called density matrices. So it's a trace class operator.
Finite dimension, not necessary.
Not necessarily. Even in infinite dimensions. Okay, but it's a compact operator, trace class operator, positive trace class operator with a trace equal to 1. So if you take any such rho and define mu of P by this trace rho P, then it has all these properties.
But what is stress in high dimension? It's just
Just same, you take some of the diagonal entries.
oh, okay.
All those things in general may not make sense, but once you have a rho which is compact, which is positive and trace 1, this product will also have a trace and it would work fine. Okay.
So previously you had rank 1 operator, now you...
This rho earlier, this was just the projection onto U, it was a rank 1 thing. Okay, so these are so-called pure states. Okay, so the general states are like this. You take a density matrix, that means you take a positive operator of trace 1 and mu, the probability is evaluated got by mu of P is trace rho P. Okay, and this is not far from this, because see any positive trace class operator here, see if I have rho positive and trace of rho equal to 1, okay, it's a compact operator, compact self-adjoint operator, so you can diagonalize it. You have a Spector theorem, you can diagonalize it, you can look at its eigenvectors, and so then you can write to this rho as summation Pj Uj. So this is again the projection onto the span of Uj, j from 1 to infinity, where these Pj's are eigenvalues of rho, and summation, so Pj's would be non-negative, and summation Pj equal to 1. Summation Pj would be the trace, it is the sum of the eigenvalues, which is the trace. Okay. Rho of Uj in Pj. This will be an orthonormal basis. Okay. So you can diagonalize rho and write it in terms of the orthonormal basis. And so in other words, this rho is just a convex combination of these rank 1s. Right? Each one is a pure state, possibly an infinite convex combination. That's all. Only difference is that. Okay, you may have all these infinitely many Pj's, but in finite dimensions you just have at most n terms. Right? It's a convex combination. Okay, so this gives you one example of a probability measure on this P of H, right? Means one class of examples. For any density matrix rho, that is what I put there, density matrix rho. A special case is this kind of thing, the rank 1 projections. General ones are their convex combinations. Okay, so these are the general states, we call them states of density matrices. And there is a famous theorem. Distance theorem. Dimension of H is greater than 2, then any mu as a whole. Any probability distribution.
So what's the spelling? GLIA something?
GLE. So any probability distribution mu as a whole, okay, on P of H is given by mu of T equal to raise rho P for some density matrix.
Any probability distribution mu on what has?
On P of H, like this. If I want a
As here.
as here, then it has to be of this. So this is it's the complete set of examples. Okay. So only one catch there. Namely, dimension of H is bigger than 2. In 2 dimensions, one can have some small
Other example.
other